Okay, so we have now obtained quite a fair bit of knowledge about the atom, about how to identify where various transitions occur, what is ionization, what is a bound-bound transition, how do we calculate the wavelength for a hydrogen transition, how do we estimate the strength or the half-life times, etc., etc. And also how do we get to the cross-sections, right? So, but when we set this up in, so to say, our tool, right, we wrote, and we will use this also, particularly in the second part today, but we sort of wrote the extinction per unit centimeters as either this mass absorption coefficient, right, times the mass density, or the cross-section times the number density or the occupation number, right? So we have spent a fair amount of time of identifying the transitions, obtaining the cross-sections, and so forth. But we have sort of left this. How do we get to the actual occupation numbers? That is the distribution of atoms that are in a specific state, say the ground state of hydrogen, the first excited state of neutral hydrogen, ionized hydrogen, etc., etc., depending on the element that we had. Now, in general, that is actually a very difficult question, because let's just consider that we have a simple atom, can be whatever, and then we have some states here, and this would be something like the ground state of one ionization state, and then we could ionize to this state, for example. But we also had various excited levels, which could be something like this, right? But then, of course, there can be transitions occurring from this to this, but if we involve this one, which would be like the number 2 state in here, in excited and in this ionization state. And there could be a transition occurring from that to number 3, but there is also ionization to that. There could also be one from this, and this one could go there, etc., etc. You can easily see that this can become quite a mess. And if we now just, this is just schematically, if we now ignore all the gas motions, the particle motions as well, and then we say, okay, we can have some sort of balance equation for some occupation number in the ith level as a function of time, then you can see, well, what do we have to really evaluate here, right? Well, whatever takes it away from that state, that's going to be dependent on how many atoms there are, right? And then it will be a sum over all other states, let's call them J, and then the transition probabilities to that state. And then that's all the depopulation transitions that can occur. And this can evolve really in the same ionization state, but also in other ionization states if we have complicated situations. Now I'm talking general. Now, in terms of populating, then of course, well, then that sum has to go over all other NJ states that can actually have a transition to that state, and then the probabilities of those to go into that. So you see that we would have to evaluate, in order to derive the population of these states, we will have to know the transition rates and then solve an equation system for all the involving states simultaneously, right? Now, these transition probabilities, furthermore, they can involve what we would call radiative transitions, but they can also involve collisional transitions. Radiative transitions we have talked about quite a bit, not so much about the collisional transitions, but you can easily imagine if you have just two neutral hydrogen atoms smashing together and then leaving, then they can be left in an ionized state, lose some energy so that the kinetic energy goes down a little bit, and then they can get excited. And then they might be radiatively de-excited from that, because, for example, if it's excited to the first excited state of neutral hydrogen, we know that the half-lifetime of that is 10 to the minus 9, so then it's just going to drop down, and then you're going to emit the photon. Yeah? That would be collisional excitation and radiative de-excitation, and so forth. Okay? So quite in general, that can set up, and we have to know a lot about the atomic physics on this. Now, to make it even more complicated, the radiative rates, in general, they depend on the mean density that is on the radiation field present. Okay? So that then quickly becomes quite cumbersome. In a lot of the literature, you see this as NLTE or non-LTE or non-local thermodynamic equilibrium. It's not a very well defined name. It basically has to do with everything that's not in local thermodynamic equilibrium. Now, what is that then? Well, also that in terms of understanding when we can have equilibrium or thermodynamic equilibrium, or at least locally, is in general, in practice, when you want to do this, not the easiest of considerations, okay? But for the purpose of this course, we can think about it in terms of this way, what we have learned, and that is that, let's say we have a situation now where we have some sort of matter, and say that the temperature now increases from outside in, right? In that situation, this is a situation that we are now pretty familiar with, and then the photons are interacting here. And then if you evaluate like the mean free path of a photon here, Lm mean free path, then typically what you can say is that if this mean free path of the photon is smaller than some typical, call it, in this case it would be, I put it on the c-axis, right? So let's just say delta c, over which the thermodynamic variables such as density and temperature changes significantly. If that one is smaller than that one, then typically we can assume that the thermodynamic equilibrium holds locally, okay? So in this case, it would be something like, let's say that we have a mean free path of this, right? But then we have like some T1 here, and then some T1 there, and then this would be delta C. And then, of course, you can say that the photons are locally trapped within a range here where the temperature and density perhaps doesn't vary too much. So you can see that close to the surface, this is certainly not going to be a good approximation. Huh? In the deep interior, though, it likely is. Remember when we did the example of the photon mean free path inside the sun, and we calculated this to be, on average, on the order of a centimeter, right? You can imagine that inside the sun, conditions don't change much over a centimeter, right? So that means that locally you can assume that this holds, and that's what we call local thermodynamic equilibrium in this case. All right? Now, the nice thing with this approximation is that the occupation numbers then take their equilibrium values. You can use the Boltzmann distributions, and you can use the Saha-Boltzmann relations to calculate the occupation numbers instead of this much more complicated situation, which is the general case of, say, NLT. So, okay, what are then these Saha and Boltzmann relations that I am talking about? Let's consider that. So, yeah, the first, the occupation number or the number density, I'm going to write it with a little n now. Yeah, so that's the number density then, occupation number. In CDS, it's 1/centimeter squared, not to be confused with the quantum principal number, which we also, the principal quantum number, which we also denoted as little n. Okay? Yeah, again, this is unfortunate in the notation, but it is as it is. Better to just get used to it. So if we now say that we have some sort of ionization state, we can call it R, yeah? And then we can ionize to another state, which is then R plus 1. Say this is the ground state of this ionization state, so that would be S equals to 1 then. I'm going to denote that by S. Then this is the first excited state, so that would be S plus 1, and so forth. That's the notation that I'm going to use today. Remember that this S was the ionization state. That's typically what we used for the principal quantum number in last week, right? So for example, if this is neutral hydrogen then the ground state would be like 1, 1, right? The first excited state there would be N12. Ionized hydrogen then would be N21, and so forth, okay? Just a notational thing. Now, then the equilibrium Boltzmann distribution, which we've actually used in one of the lectures before as well, says that for any given RS8 here, the occupation number is proportional to the probability of finding the atom, the molecule, in that state, and that is proportional to e to the minus the energy divided by kT. And in the terms of our picture here, and in terms of the Boltzmann excitation formula, this is the excitation energy. Okay? So let's just apply this, and then we can see what is now the N1, 2. We have a proportionality here, and I forgot that it's of course also the degeneracy GRS of this. My apologies for that. Okay? So NY2 then is going to be proportional to the excitation energy of that, N12. If that is hydrogen, for example, we know that's 10.2 electron volts. The difference between this and this state in hydrogen corresponds to a photon of 1216 angstrom. The Lyman alpha transition, we know that by heart now. This is going to be proportional to that, but we're going to divide it through, because the constants are the same, with the number densities there, and that doesn't have any, so this would just then be G21 divided by G11 e to the minus delta E to 1 divided by KT, which if this is hydrogen, for hydrogen, then your delta E to 1 would be then 10.2 electron volt. And this is your Saha formula. No, your Boltzmann formula for excitation in that form. You can also choose to sum overall states here, such that N of R then, of course, is the sum over all S states that you have, NRS. So you can see that that is going to be proportional then to the sum over all these dual weights, and then all the excitation energies like that. This you typically call then the partition function for the ionization state R, because it's the sum over all excitation states S. And then you see that we can divide through by that to obtain also this formula of the Boltzmann ERS divided by KT divided by UR, where UR is a rotation function. Okay, so that's actually the Boltzmann formula. But let's take an example. Let's do an example so we just get used to this a little bit, okay? Let's try to evaluate if this were all that it is, you know, then at what temperature would N12 equals N11 of hydrogen? If this excitation, Boltzmann excitation formula were all that it is. That is, at which state, at which temperature would we have as many atoms in the first excited state of hydrogen as in the ground state? Okay, we're going to evaluate that. I'm going to do it here on the blackboard. You can work a little bit there, and then we'll see what we get through. Okay? So this is done now here for you, where actually the only, so to say, problematic thing in this little exercise, of course, is that you have to translate the electron volts to the appropriate units wherever you have your constant K in, right? So be aware of the units again. That's normally the case when we do these type of exercises, as you know. In this case, you have the conversion between electron volt to CDS in the course booklets at the end, where you have a lot of these conversions. The point here is that this then would happen at 85,000 Kelvin. So if we had a gas of 85,000 Kelvin and Boltzmann's excitation formula were all that it is, then in that phase we would obtain as many atoms in the first excited state as in the ground state. In practice, however, this never happens in principle. Why is that? What have we forgotten? Anybody? What have we forgotten to consider here? What happens when we start to increase the temperature more and more? We have said, okay, we can excite, but what can we more do? We cannot just excite. What happens if we push in a photon with an energy above 13.6 electron volts? We don't excite, we ionize. So in reality, what happens is that way before, typically 85,000 Kelvin, when this is reached, we start to ionize away neutral hydrogen. Yeah? So that in practice, almost everything that is neutral remains in the ground state. This is quite general. It's almost always the case that whatever we have, either for hydrogen, yeah, it's going to be in the ground state of neutral, or it's going to be ionized. And then it's going to be a small amount in the excited states. And those are extremely significant because they give rise to all of these spectral lines, right, and features in the spectra. But when we look at the sheer numbers, that's how it behaves. So what do I mean by this, and why is this significant? Well, so here is just a sketch of the occupation number of 1, 2, first excited state of hydrogen, as a function of, say, temperature. Now, according to the Boltzmann excitation formula, this will just increase, right? At basically nothing, at low temperatures, there won't be anything, but then it will just increase, like this, quite steeply. However, what happens is that at a certain temperature, we're going to start to ionize as well. And then you have a competing effect that instead of getting up in the excited state, you ionize away. So then, instead of continuing to increase the population of N12, you get a balanced situation. So you actually reach a peak. And after that, you sort of drop again. This is just a schematic now. We will look later during the course in some calculations of this also. Actually, after today, you will be able to do this calculation yourself. So typically, you reach a peak. Now, the interesting thing is that this peak here, if you just evaluate it with the equilibrium Saha Boltzmann relations, and for, say, a density of stellar atmosphere, like, say, then this occurs around 10,000 Kelvin, okay? And that has actually a very important application when it comes to stars, namely the so-called Balmer jump. So the Balmer jump is a feature in the spectrum. The Balmer jump, we know what it is from previous classes. It is the ionization, but not from the ground state, but from the R equals to 1, as we call it now, but S equals to 2. So the first excited state of hydrogen to this, yeah? Remember we evaluated this, we learned with the Bohr atom or with the Schrödinger, the solution to a Schrödinger equation, how to calculate the energy here. And then this we call the Balmer jump, yeah? Now, of course, the strength of the Balmer jump depends on how many atoms there are in this excited state. Because if there aren't any atoms there, then of course, yeah, you can't do it. You know, even if you have the right frequency of the photons, you still can't do it. Now, since this peaks at 10 to the 4 Kelvin, it turns out that for stars which has that around that temperature on their surface, those are the stars that we call A stars. Then this feature, the Balmer jump in the spectrum, is very, very prominent. Then as we go up in temperature, more and more starts to ionize, this starts to decrease, and also the Balmer jump start to decrease its visibility in the spectrum. Vice versa, when we go down in temperature, the same thing happens. So you get a peak. And actually, this is classically a very important temperature indications of stars. And you can use that to derive the temperatures of stars. Right? It's also probably the feature in the spectra of stars that is most significantly different from a black body distribution. That is, when you look at the broad energy distribution from stars, they sort of look like black bodies, but the Balmer jump you can quite often see, yeah, in the spectra. We will look at some spectra on that during some class. So that's a direct application of this here. So what is this ionization then that I'm talking about? Well, that here proceeds with the Saha ionization formula, okay? Now, what we have to remember here is that now, if we have something like R, yeah, and then we go to r plus 1, then of course we have ionized, so I have rid ourselves of a free electron. So our balance equation here involves another particle. That was not the case in the excitation case, right? It remained bound. But here we have rid ourselves of an electron, so we have the balance here. So when we set this up now, we have to take that into account as well. That is just using the analogy of the Boltzmann before, we set it up like nr plus 1, but we have to take also the occupation number of the electrons into account. And then we divide it by nr, and then these occupation numbers are also going to be there. And then in this factor, when we evaluate the energy, yes, we will have the ionization energy then, which we again know. We know how to calculate it for at least hydrogen, right? But the thing with the difference, as we have discussed, between the bound-free and the bound-bound things is that we don't have to come in exactly at the right wavelength now. You know, there is a probability for absorption even if photons have a little bit of an offset in terms of their energy. At the one side, they have to have more energy. Typically, it goes something like this. Shown you this before, that the transition probability for ionization goes up, and then it's strongest at the peak, and then it drops dead. But also here, the photon energy would increase in this direction, right? Here, of course, it drops dead, but this is typically power law of 3 or something like that. But for our discussion here today, this just means that the resulting electron can have some kinetic energy associated with it, which has to be taken into account. And then this gives typically then the balance for ionization with free electrons that have a resulting kinetic energy in some interval Pe plus then dP. Then we will have to actually integrate this over all possible dPs. Well, no, over all possible PEs, so momentums for the electron. And that we could do with the Maxwell distribution. We're not going to do that then today, though. I'm actually just here, I schematically give it, and this is one of the cases where I refer to your course in statistical physics, where you derive the Saha relation more rigorously, and we will actually here, because we can't cover everything, I will write down the result. The resulting distribution for nr plus 1 Ne divided by, this is in the ground state now, Ne divided by nr r, and in the s equals to 1 state is going to be 2, that's the degeneracy of the electron in the ground state then, and then G, of course, R plus 1, 1, that's the degeneracy of the atom, and then 1, and then we have this factor here, 2 pi MEKT H squared, 3 half, and then E to the minus E ionization divided by KT. And this factor that comes out here is a reflection of this. Okay? So what you can see here in this formula is that first, if you have the electron number density, you can see that the right-hand side here is only a function of the temperature. In general, of course, you also have to then calculate the electron density. Yeah? So that's where the density dependence will come in later. Now, you see that you still have the exponential factor here, which is a reflection of the Boltzmann distribution. And that is, of course, what makes it so difficult to excite to Boltzmann, and this term also would make it very difficult to ionize, right? We will have to go to very, very high temperature. But in practice, this here works as a sort of an works at lower temperatures. And this factor here is the reason why you start to get ionization way before, at way lower temperatures than would be predicted by just applying the Boltzmann distribution, the exponential here. And that is this one. Now, physically, you can say that that just is a reflection of the tail of the distribution. Because you come in terms of here, you can see it as you come in with the distribution of speeds of the electrons. And while those may reflect, on average, the temperature, there is a high-speed tail there. And that high-speed tail then can start to ionize way before the mean can do it, right? Now, after the break today, we will see how we can interpret it in a similar way using the high energy tail of the Planck distribution function, when we try to understand when and why the universe got ionized or recombined at the temperatures as it did. Okay? So you think about the tails of the distribution, and you have some possibility for ionizing there, which goes at much lower temperatures than would otherwise be possible. All right. I'm going to leave it at, we're going to use this formula now during the rest of today's class, and then we're going to go to this application which I have already alluded to. But first we'll take a break. We'll take a 5-minute break, yeah?